Hi everyone, I'm John Dickinson. I'm Chief Commercial Officer at Equal Experts, and thanks for joining us this evening for our next expert talks. And so this evening I'm thrilled to introduce Dave Farley. Dave is a pioneer of continuous delivery. He's a thought leader and expert practitioner in continuous delivery, DevOps, TDD, and all things software development. Dave is the co-author of the Jolt award-winning book on continuous delivery. And if you want to see what Dave's up to, you can find him on YouTube. He's putting out new videos on continuous delivery every Wednesday. So if you just search for continuous delivery on YouTube, then you'll find him. And there's loads of great content going up there. As I say, it comes out every week on a Wednesday. In fact, I think there'll be one released while he's talking this evening to you all. So the magic of social media automation. So this evening, Dave will be talking about the rationale for continuous delivery and how it changes the economics of software development for some of the biggest companies in the world, whatever the nature of their software development. So I want to say welcome to Dave. Thanks very much for joining us.
Thank you, John.
Dave, we're going to run the talk a little longer tonight than we normally would. So I think Dave's talk is about 60 minutes. And after that, we are going to run a fishbowl. We have been doing more experimentation with webinars to see how we can make them more inclusive and turn it into a more social discussion. So if you have any questions that you would like to be discussed in a fishbowl type scenario, so a panel will be joining us, and then anyone from the audience can join that panel as we go through the discussion. If you have any questions for Dave or for the panel to be picked up in the fishbowl, then just put them in the Q&A tab. So there is 2 speech bubbles at the bottom with Q&A in the Zoom application. So if you click on that, and you can put your questions in there, and I'll be reminding people in the chat as we go through the talk. So that is enough from me. With that, I'm going to hand over to Dave and say thanks very much, everyone, for joining, and take it away, Dave.
Thanks, John. Thank you for the introduction, and thank you, everybody, for joining us this evening. My talk today is, as John said, is about the kind of rationale for continuous delivery. I just want to do a little bit of preamble just to kind of set the scene. I think that in software development, we tend to get obsessed with the idea of change a little bit. We see ourselves as an industry of change, and it's a fast-moving place. Technology moves quickly. Our ideas, move quickly. But I think that there are different kinds of change, and I think that there are some ideas that change really rapidly, but to be honest, aren't that important. New languages come along all of the time. Different frameworks and tools come and go, and are in fashion for a while and not for another. And then there are other ideas that are more durable. I hope without too much hubris, I believe that continuous delivery is in that second category. I think that continuous delivery is an important change in the way in which we can think about and organize ourselves for software development. And my aim over the next hour is to try and convince you that I'm saying that not just because I'm trying to sell you a book or some consultancy or something, but because it's a useful idea to you. So I'm just going to now share my screen so you can look at my presentation rather than my face, which is probably a benefit from your point of view. So here's my screen. I hope everybody can see that okay. And let's start getting into thinking about continuous delivery. So I think that the state of software development, if we look at software development, it's an interesting practice, and it's difficult to measure. Over the years, there have been many of these kinds of studies that have looked at software development and done different kinds of surveys of software development performance. And although these are not scientifically rigorous, they tend to tell a fairly consistent story, and it's pretty depressing. This last one is kind of amusing if you're a fan of Schadenfreude. In a study of nearly 6,000 large-scale projects with budgets of over $15 million, 17% of them went so badly that they threatened the existence of the company performing those projects. That's pretty scary and pretty terrifying. If software projects were normal things, there ought to be a normal distribution of software project success, as many software projects ought to be delighting their users, finishing ahead of schedule and under budget, as those that finished over budget, behind schedule, and annoyed their users. But I don't think that's what we perceive as normal in our industry. I think what we perceive as normal is much more like the red curve here. And that has some important implications. It means that the way in which we undertake new software projects is warped towards the, trying to consider about the failure. We agonize over preparing for the software project and budgeting for it and all of those sorts of things. There's another take on this. If it ought to be a normal distribution of software project success, that's kind of a mathematical statement. Why isn't it a normal distribution? Why is it so warped? It would suggest that we've got the model wrong. If we had the model right, then there'd be, a normal distribution of project success, and there isn't. And then we get into this beautiful little GIF animation of two different takes on the orbits of the planets in the solar system. I'm a bit of a physics nerd, and I love this little simple picture. This depicts two different models of how the orbits of the planets work in the solar system. On the right-hand side of your screen is the geocentric model for the solar system. This was the model that was held by humanity for tens of thousands of years, and it's kind of obvious why. We're stood here, we're obviously stationary, therefore everything in the sky is revolving around us. And that makes sense when you look at the stars and the moon and the sun and all that. And then there are the planets. And the planets do all of these crazy things in the sky. They wander about, sometimes they go backwards across the sky, sometimes they go forwards. And at the time, people struggled to be able to describe what was going on. The word planet is derived from ancient Greek for wanderer, because these weird things in the sky wandered around seemingly in random directions. During this period of time, some of the most complicated devices that human beings built were built to try and predict these planetary orbits. Complicated clockwork devices before we really used clockwork for almost anything else, called orreries. Now, there's a problem with this worldview or solar system view. If you live in the solar system on the right-hand side of the screen, Newton can't come along with an inverse square law and essentially invent science. Einstein can't come along a few centuries later and come up with bendy sheets of space-time and come up with general relativity. Those ideas do not flow from this view of how the solar system works. In order to achieve those things, in order to make progress, in order to be able to think certain kinds of ideas, we have to have a paradigm shift. We have to completely swap our view. And what happened in this case is that Copernicus came along and Galileo later on, and they said, no, we've got it wrong. It's the sun that's at the center of the universe, which is mistaken, but it's a more accurate approximation. It's the sun at the center of the universe and everything revolves around that. And when that happens, the maths becomes so simple that even I could kind of, plot the orbits of the planets using that kind of maths. Now Newton can come along and come up with his inverse square law. Now Einstein can come up with bendy sheets of space-time. So why am I going off on this nerdy rant about solar systems? It's because I think this is almost this most beautiful representation of the idea of paradigm shift, and I think that's what we're talking about. I think we're talking about when in software development terms. I think that most software development in the world inhabits in some form or another a form of solar system on the right-hand side. People are viewing things through the wrong lens, and they're in the wrong paradigm. That has lots of implications. It means that if we want to work in the new paradigm, we've got to break the rules of the old paradigm. It means that it challenges conventional wisdom and thinking about all sorts of different things. And that's difficult. That's a difficult thing to undertake. So I want you to keep that idea of paradigm shift kind of in the back of your mind when I'm talking about some of this, because I think that what we're talking about does represent a fairly radical shift in viewpoint. So I would argue that the state of software development has kind of been less than optimal for quite a while, if we look broadly across the industry. But I would also argue quite strongly that there are significant signs of change. I think over the past couple of decades, more than the preceding 30 years or 30 or 40 years, we've really seriously made some progress on what really works. I think that now we know that works. We've got measurements of things that work. We're going to talk about that a little bit later. I chose this picture with some care. This is a motorbike with a jet engine attached. It was clearly not mass produced. It's not beautifully engineered in the sense of a production BMW motorbike or something. It was built in somebody's shed, but it is a motorbike with a jet engine attached. And I think that's probably where we're at the moment in terms of software development, tooling and practice and so on. We know what can work. We can do things that are an awful lot better than what went before, but it takes a little bit of handcrafting. So what have we tried? It's interesting to kind of look at the way in which we got to where we are. And I think that one of the huge mistakes that we've made, the thing that is at the root of that problem of paradigm shift, is that we tried to adopt the models from other industries that weren't really applicable. If you are building something like a car, then designing that car for the first time is a complicated problem. But mass producing that car so you can make thousands, hundreds of thousands or millions of them to a budget is an incredibly more difficult problem. That is the production problem and the kind of problem that things like production lines were designed to fix. The problem is, the difficulty is that we never have that problem in software development. We spend all of the time kind of designing something, and when we want to mass produce it, it's just we just clone the bytes that we've created that represent the system. It should be free or almost free if we get the production of those things right, because copying bytes is almost free. So the mistake that we've made is trying to apply production style thinking from the physical world and apply that to software development. So in response to that kind of thinking, we came up with waterfalls approaches, V models, and so on. We tried to divide problems up into segments so that we could work on those pieces, and ended up building siloed organizations. We tried working in more iterative, parallel ways using things. This is a picture of the Rationale unified process from the late 90s. And we've tried using sort of more agile project management disciplines. All of these kind of represent sort of a learning process as we kind of figured out what works and what doesn't work along the route. We tried adding more engineering thinking to our development and tried some extreme programming. We tried hiring really smart people and putting them in a corner somewhere. And we tried hiring young smart people because they're a bit cheaper. And we tried hiring young smart people in other countries because they're a little bit cheaper still. And all of these have kind of had an impact on the way that we think about and practice software development, but haven't really solved the problem. There's no kind of slam dunk here, really. When you look back at it from a historical perspective on the evolution of software, this is an interesting document. This is the document that introduced the concept of waterfall to our industry, to our practice for the first time. This was originally published for an IEEE conference in 1970 by Dr. Winston Royce. And Dr. Royce was a smart guy. So this was a 15-page document. It was published as part of the conference proceedings. And this very, very famous diagram, which nearly everybody has seen some version of, was on page 2 of the document. You can kind of imagine flipping through the conference proceeds and getting to page 2, seeing this very prominent diagram, saying, oh, yeah, I see what he's talking about. You don't bother reading the rest of the document because you haven't got time, so you head off to the pub or whatever else and think, oh yeah, I'll tell my team this next time I see them. That's kind of a shame, because if we had read on to the next paragraph, we would have seen this. I've expanded it so you can see some of the key phrases. The implementation described above is risky and invites failure. The testing phase, which occurs at the end of the development cycle, is the first event for which timing, storage, input-output transfers, etc. are experienced as distinguished from analysed. These phenomena are not precisely analysable. So the document that introduced waterfall to our industry, which is really a production line style process, was really saying, whatever you do, don't do waterfall. That would be crazy. This is the document, this is the diagram that Dr. Royce was really recommending. This is on page 15 of the document, and the way that the document is structured is he tries to build this diagram additively. He kind of evolves his thinking through the document and gets to this. So the waterfall that he was kind of on page 2 was the kind of before picture. This is the after picture. This is what he was really saying. And this is a really interesting picture. It's not so instantly appealing as the first one, I concede. But if you read this with the benefit of 21st century hindsight, it says things like, involve the customer, do the job twice if you can. Testing must be planned, controlled and monitored. You should establish feedback loops from testing into software design and from software design into software requirements. I think with the benefit of that 21st century hindsight, you'd probably characterize this as some form of agile process. So the document that introduced waterfall to our industry was really recommending an iterative, exploratory, agile process-ish. So what does that mean? So here's kind of just a meme I want to plant in your heads. So here's a picture of a nasty accident. There's a car has fallen off the quayside in the water. This is in the west of Ireland. You've hired a truck to pull the car out. So what happens next? So you rent the truck and you lift the car out. Oops, what do you do now? If you're playing along, I can hear you saying, rent a bigger truck. Quite right. What's going to go wrong there? There we go. Einstein defined insanity as doing the same thing over and over again and expecting different results. I would argue that we've been trying for about 30 or 40 years, we've been trying to make waterfall approaches to software development work, and they simply don't. They're the wrong model for software development. So let's start thinking about what it is that we really need, what we really want. And I would suggest that it's something like this. I think that any organization that practices software development for any purpose would like this. They'd like to be able to have an idea. They'd like to be able to get that idea out into the hands of users in the form of valuable software, or working software at least. And then they'd like to figure out whether the software is useful to the users. They'd like to see what the users make of the software. And they'd like to be able to do that quickly, efficiently, reliably. So that seems like a good place to start. If we want to kind of reboot our approach to software development, that seems like a nice place to start. So what would it take to optimize to make that loop efficient? So I want to pose a question. What's the most successful invention in human history? And here are some pictures that are meant to mislead you. If you're playing along, I can hear probably saying fire and language and all those. Those are good ideas. I think my idea, if you haven't already come up with it, beats them all. I think it's this. I think it's science. If you think about the impact of science on our civilization. So science, as we would recognize it today, was invented about 300 or 400 years ago. That's all. As a species, we have existed for somewhere between 200 and 300,000 years. That's That's where the dates are at the moment, based on science. So we're about 200,000-year-old species. Agriculture didn't start until 10,000 years ago. So the vast majority of our history was nothing happened very much. We made some stone tools. You know, monkeys make stone tools. We made some stone tools of various kinds for about 200,000 years. And then we came up with agriculture, and for about 10,000 years, we were kind of an agrarian civilization. And then about 300 or 400 years ago, some crazy people came up with some ideas about science. And I'm not talking about space shuttles and large hadron colliders. I'm talking about this, the scientific method. They came up with a way of trying to avoid fooling ourselves. And if you think about it, the application of this kind of thinking is really the distinguishing characteristic between our civilization and all those civilizations that went before. The growth since over that last few hundred years is explosive. And particularly through the 20th and the 21st century. There's data that suggests that all of human knowledge is currently doubling every 14 months. That's a staggering proposition. We are doubling all of our knowledge on that. We're on this exponential curve of learning, and that is completely down to the application of the scientific method. When we start applying the scientific method to practical problems, we call that engineering. And so part of my push is to drive us towards a more of an engineering discipline than a craft-based discipline. Craft is better than production line thinking, it's a better fit, but engineering is better than both of them. So here's what Wikipedia says the scientific method is. We make a guess based on experience and observation. We propose an explanation based on that guess. We make a prediction from the explanation that we propose, and then we test the prediction. That's it. We will just go over and over and over that, and that's the thing that ends up with us being able to build spaceships that go to the moon and large hadron colliders and hopefully vaccines for things like COVID-19. This is the mechanism that allows us to do that kind of rational thinking. So why am I talking? This is so obvious. This is kind of motherhood and apple pie. Why am I talking about this? Think for a moment about your own work in software. If your work is anything like the vast majority of my career, this is not what I did. This is not what I did for the majority of my career writing systems. We would guess about what it was that our users want. We'd guess about a design that might fulfill those needs. We'd guess about whether that design was going to be fast enough, resilient enough. We guess about whether there were any bugs in it before we're into production. We didn't measure any of those things. We didn't make predictions of where we would end up with those things. We didn't measure those predictions. We didn't really play this game at all. I would argue that software development is one of the more difficult tasks, activities that human beings undertake. We deal with this ephemeral, hard to understand stuff, this software. It's hard to get your grips on. There are some profoundly difficult things in software development. Things like distributed programming and concurrency are kind of up there, world-class problems alongside ideas like quantum physics when you really start digging into those sorts of ideas. These are deep, deep problems that we professional software developers play with every day. And yet, we're doing this incredibly difficult thing, and yet we don't apply humanity's best problem-solving technique to solving those problems. So I think that step one on our journey towards making that loop from idea to software in the hands of users so we can figure out whether the ideas are good is to start doing things more scientifically. Let's look at a bit more data. I'm going to whiz past this reasonably quickly because I want to get into some of the stuff. So the surveys, as I said before, these are not deep, but the surveys tend to tell a fairly consistent story. This is one of the more optimistic surveys of software performance from Scott Ambler, who's been collecting data from the industry for many years. And basically, this is my organization of his data. The bottom line are kind of traditional approaches to software development, mostly waterfall, planned, staged approaches. The top line are more iterative approaches, and immediately we can see that there's a difference in the rate of success. The green blobs are meaning that the software was on time, on budget, and doing stuff that people wanted. The yellow blobs was 2 of those, and the red blobs was 1 or less of those. So, you know, this is quite optimistic. This is saying actually, you know, we can do quite well. Lean stands out as the best of those approaches. So it might be worth just looking a little bit at what lean is about. Lean thinking is about delivering things quickly. One of my favorite kind of elevator pitches for what lean is about is lean thinking is really trying to get the maximum impact for the least amount of effort. We're going to concentrate on trying to optimizing the whole, doing quality work, eliminating waste, so that we can kind of get the maximum output for the least amount of effort. We're going to try and reduce waste in various ways. I'm not going to go through all of those ways, but I want to call one particular form of waste that lean practitioners identify, which is overburden. If you are doing too much work, that's a form of waste. Part of my career as a software developer was working in high performance financial systems, building low latency exchanges and trading systems. And when you work in that kind of world, you become obsessed by ideas like queuing theory. And if you think about it, a software development team in information terms, of course, there are clever people in the middle of it, but in information terms, a software development team is kind of a queue. You're going to have requirements coming in one end and hopefully working software coming out of the other end. So how do you optimize the throughput of a queue? Let's just briefly play that thought experiment. Well, you could try putting nothing in the queue, and you're not going to get very far with that in terms of optimizing the throughput, because nothing's going to come out. You could try fully loading the queue, making sure that the queue is always full. And if you think about it in software teams, that's how most planning works. Most planning works at trying to identify the capacity of the team and making sure that you're pushing as much stuff through that team as possible. So what happens when you do that with a queue? Well, you complicate the system. It means that the things that are trying to put things into the queue now have to cope all of the time with the queue being full. It means that you're building a race at the point at which you're trying to put things into the queue. It means that the things taking off the queue are having to work flat out all of the time to try and process the queue. It means that there's no scope for racing ahead and beating things that are in the queue, because the queue is fully loaded. You've got to wait until everything is in the queue is out before you can start work on the next important thing. Think a little bit about how that works in a software team. I work as a consultant advising organizations on how to improve their software development practices, software engineering, in the frame of DevOps and continuous delivery. And my impression is that the vast majority of certainly larger organizations where I tend to work completely buy into the idea of optimizing to make sure that the queue is always full. And if you do that, if you're building to make sure that you're optimizing for feature delivery, it means that there's no slack in the system. There's no ability for the team to undertake work that can make them more efficient and process more work. And so what tends to happen is that teams get slower and slower and slower and tend to grind to a halt through that process. Now, going back to my kind of idealistic picture of what happens with a queue, if you do the numbers, that there are things like Little's law and Amdahl's law and all those sorts of things that you can kind of start doing a mathematical analysis of kind of simple queues in information terms, it's not as simple as I'm making it sound. It's more complicated. But for most simple processes where there are limits to the degree of parallelism in those processes, the numbers tend to come out in a reasonably consistent range. If you want to maximize the throughput of the queue, you keep it loaded to somewhere between 60 and 70% of its capacity. So if you want to make your development effort more effective, you should limit the amount of effort that's being demanded of a team to about 60 or 70% of their capacity. That will allow them to work more effectively. It will allow them to concentrate more on higher quality work, which in turn will mean that they'll spend less time fixing defects in production, and so on and so on and so on. You get some huge knock-on advantages from focusing on that kind of thing. And then Lean goes on to talk about amplifying learning, making decisions late rather than early. You know, one of my friends used to say, you make decisions at the last responsible moment, and empowering the team, allowing people working within a team to make decisions that affect the way in which they do their work. What we're really talking about here is establishing feedback. We're talking about trying to make the processes fast and efficient. We're trying to optimize from having this idea to getting useful software into the hands of our users. And there are other feedback loops. We're going to use the fast cycle feedback of unit testing and test-driven development. And then in between that, we're going to use kind of BDD ideas and specification by example to acceptance-based testing to evaluate things from the point of view of users of the system and get really fast feedback to get to a repeatable, reliable process for releasing software. As you can probably tell from the nature of my conversation, I'm a bit of a popular science nerd, and this is one of my heroes, Richard Feynman. And the thing about Feynman, he's just wonderful to quote on the topic of science and the philosophy of science. This is one of my favorite quotes. It doesn't matter how intelligent you are. If you guess, and that guess can't be backed by experimental evidence, then it's still a guess. So we should be trying to move out of guesswork and into experimentation. So that's kind of the first key foundation stone in what it is that we're trying to do. The next one is really about speed and how we think about that. And that's the idea of cycle time. Cycle time is an interesting idea. If you imagine for a moment making a single line change, the simplest change that you can imagine to your production system. And then imagine if you were to follow your process, whatever that process might be, that one line change going through that process. So somebody's going to identify that this is required. Somebody's going to capture that, you know, in a requirement in sign. Somebody's going to allocate that to a team. Somebody's going to, you know, pick that up and decide how they're going to design it, how they're going to test it, and so on and so on and so on. If you measure how long it takes to go from idea to a releasable thing, that's the cycle time. Well, actually, that's the lead time. But if you go from idea to working software in the hands of users, that's the cycle time. And thinking of this simple change is like a die trace analysis of your development process that allows you to measure it. Now, I'm going to show you two cycle times. This is the first one. This is from a project that I worked on. Both of these are projects that I worked on. The first one was an order management system in a bank. It's long enough ago that I could probably name the bank. We did a project for Barclays Bank many, many years ago, and they had a cycle time where it took 103 days on this one project to make a single line change if they followed their own process. If you have a 103-day cycle time, you don't really have feedback. It's too long. If somebody comes to me 103 days later and says, Dave, you just broken production, I have no idea. Oops, sorry, I pressed the button twice. There we go. This second example is from a project that I worked on. It was one of those kind of career-defining projects. It was a wonderful project. I was employed to lead the engineering team for this project when in the middle of writing the continuous delivery. So this was kind of a greenfield experiment in what you could do with continuous delivery if you had the freedom to do it. And we were building one of the world's highest performance financial exchanges. In terms of scale of the system, the picture here, the cycle time here, is for the entire enterprise system, which was probably somewhere like 15 to 20 times the size and complexity of the order management system in the example above. For the entire enterprise system, when we built our exchange, we could make any change to our enterprise system to the point where it was releasable into production with no more work and get an answer back within 57 minutes whether that change was releasable or not. That's game-changing. That is completely, radically different to the line above. It just changes the way that you think about nearly everything. I'll give you a silly example. we decided at one point that we didn't like the commercial terms that we had with a relational database vendor for a data warehouse that we had. And so we decided we were going to use one of the open source relational databases instead of the one that we were paying for. So we went and chose which one we were going to use. We downloaded it, the installation. We scripted the installation so that it would work with our automated deployment tools and infrastructure as code tools. We put the change through our deployment pipeline, and it broke a couple of tests. So we kind of backed out that change, we looked into the tests, we fixed the problem, we resubmitted it into our deployment pipeline. 57 minutes later, we got an answer saying all the tests had passed. The next time we went into production, it went into production with the new version of the database. Now, what I just described to you in many organizations would have been a 6 or 12-month exercise, even if you could have done it. In the whole of the story that I've just described to you, we did in the morning. We did it in under 4 hours. We picked up the story and decided we were going to do it, and all of the work that I described took under 4 hours. That's a very, very different relationship that you have with work. If you take these two ideas seriously, the idea of working to reduce your cycle time to the point where you can get to a genuinely releasable outcome multiple times per day, and you apply the kind of scientifically rational thinking that I described earlier on in my talk to achieving that end, then just that idea, going to the faster cycle time, pretty much drives out all of agile thinking, all of lean thinking, all of DevOps thinking, and all of continuous delivery thinking. You can't have a 57-minute cycle time if your teams are too big, because the communication overhead will slow you down too much. You can't do it if you've got siloed teams with dependency management, because the handovers will slow you down too much. You've got to have a great story on automated testing, automated deployment, configuration management, infrastructure as code. All of those things must be done well. So this is an incredibly powerful tool. I use this in often big, complicated organizations, these two ideas to drive change in the organization. You just start by trying to reduce the cycle time. And at first, I had a client that hadn't released any software into production for 5 years. And we worked so that they could get to the point where they could release change every 6 months initially. Now they're in a change, they're producing releasable software every week. They've still got a way to go before they get to 57 minutes, but they're working on it. And the cultural change and the technology change is just radical as a result of being able to achieve that kind of outcome. So these are two kind of key ideas. These kind of important principles. Let's just talk a little bit more about what we're talking about when we start really defining what we mean when we talk about continuous delivery. The phrase continuous delivery comes from the Agile Manifesto, which said our highest priority is to satisfy the customer through the early and continuous delivery of valuable software. Have an idea, get the idea out into the hands of users and figure out what they make of it. It's kind of the logical extension of continuous integration, the development practice, where as developers, we just get fast feedback that was popularized kind of at the start of the century. It's a holistic approach to development. The way that I talk about and advise my clients to think about continuous delivery is you're optimizing to get to a releasable outcome multiple times a day. You do whatever it takes to achieve that. If you need to be testing security to achieve releasability, you test security. If you need to be changing the way in which the teams are organized, you change in which the teams are organized. If you want to change the way in which projects are planned, you change the way that projects are planned. Because the value of this is so high, it's worth making almost any change. So you take this very broad view of what's the levers that you can pull in order to achieve these outcomes. A good mental model for this is that every time that we commit a change, we are giving birth to a release candidate. And then the rest of our process, the job of the rest of our process is to prove that that release candidate is not fit to make it into production. That sounds wrong at first, it sounds backwards at first, but this is another of those lessons that we can learn from science. It doesn't matter how many tests I have, I can never prove that my software is good. But if I have one test that fails, I know that my software is not good enough. and therefore I can use that. This is the idea of falsifiability. This is the idea that Karl Popper kind of characterized in the 1930s that had a huge influence on the way in which we practice science through the 20th and 21st century. So we can use falsifiability in software. We can use our evaluation of systems as a falsification mechanism. One test fails, we throw the release candidate away, and we commit a new change that either reverts the change that failed or corrects the mistake that we made. Done means in the hands of users delivering value. We're not going to have kind of artificial measures. We're not really done until the software that we're making is useful. If we want to do those things, we're trying to, so we need to get to control the variables. We need to be able to start to really, if we want to be more experimental, more scientific, we need the outcomes to be more deterministic. So that means we've got to create a repeatable, reliable process for releasing software. That means we've got to automate pretty much everything. And if we're going to automate everything, we've got to keep nearly everything under version control. We've got to take quality seriously. We've got to bring the pain forward and do things more frequently so that we can kind of learn and adapt and change the way that we're working to be more and more efficient. Remember, we're trying to optimize to have the least amount of work for the maximum impact. And you don't get to do this without taking a really serious approach to continuous improvement. We're looking to, this is a huge change for most organizations. It's culture defining. It changes it shakes up the culture of an organization to be able to do this. And you don't do that in one big leap. You don't do this by reading a book or going to, listening to a talk like mine or going on a training course, or this is a thing that you do over a long period of time. This changes the way that you think about software development forever, and you do this as a series of small steps. That's how this works. This is an old quote, but it's me showing off a little bit. If agile software development was the opening act to a great performance, continuous delivery is the headliner. I think there are some good reasons for that. This is a quote from Forrester Research, not long after my book was published. I think there are some good reasons for that, because what we're talking about is genuinely trying to apply some more scientifically rational ideas to achieving better outcomes with software. So we can think of this as a true engineering discipline for software. Now, I'm going to whiz through this fairly quickly, but this is the idea of a deployment pipeline. Continuous delivery is about more than just the technical processes. You need to think about the cultural impact, the organizational impact, but the technical impact allows you to drive quite a lot of those changes. And so it's a useful place to think about and to do work. So if we want to achieve that repeatable process, if we want to get to that releasable thing multiple times a day, here's a kind of outline of the way in which we undertook that when we built our financial exchange. So we have some developers and they commit some change to a version control system of some kind. At this point, what we're interested in is two things. We'd like a really fast answer of, have I messed something up? And we'd like a reasonably high level of confidence if this answer is no, you haven't messed anything up, that's a decent answer. So we'd like to be able to get some level of some sense of the quality of our system very quickly and very efficiently. And those are kind of in tension with one another. In order to do that, what we're looking for, I generally advise my clients that what you're shooting for with the commit cycle is you're looking for feedback in under 5 minutes with about 80% confidence that if all of these tests pass, everything else is going to be fine. So that means that it's starting to tell us things about the nature of the testing that we can carry out in this tiny time window. It means that we probably can't afford to start up the system that we're working on. We can't really afford to be writing out things to disk because disk is too slow. We can't be talking across a network too much because that's too slow. So really what we're talking about here are kind of unit tests for the vast majority of tests, not exclusively, but highly efficient technical tests of the technical quality of the software. These are best produced as an outcome of test-driven development, in my opinion. And when you do that, you can kind of get hundreds of thousands of these things that will run in that 5-minute window, and therefore build up a good level of quality. So the commit stage is going, when there's a commit, it's going to trigger the commit stage, it's going to build the system, and it's going to run a suite of tests that are going to very quickly give us this kind of 80% level of confidence, ideally in under 5 minutes. When the commit stage is finished, remember, we're trying to do a lean process. We're trying to minimize the amount of work. So we've just spent a bunch of time, if we've got a compiled language, we just spent a bunch of time compiling the system. And we've just run a whole bunch of tests against that binary version of the code. We don't have to build it again, because we might introduce an error. We might compile it with a different version of the compiler, or even if that's not the case, we don't want to waste time by recompiling stuff we've already compiled. So what we're going to do is that we're going to store the output of that commit stage as a binary artifact, and from now on, that's what we're going to deploy, and that's what we're going to test. Now, I'm a huge fan, a huge proponent of test-driven development. It gives us as developers great insight into the quality of our code, and it's a useful tool to drive higher quality design in our systems. I haven't got time to explain that statement, but if you'd like to know more, have a look at my blog post or my YouTube channel. The next thing, though, what it doesn't tell us is it doesn't really tell us whether the system does something useful. It identifies the technical quality. It answers the question, does the software do what I as a developer think, does the code do what I as a developer think the code is doing? It doesn't answer the question, does the software do what the users want it to do? So we need a completely different set of tests from a completely different perspective to answer that second question. And in continuous delivery terms, in the continuous delivery book, we call those acceptance tests. These are automated acceptance tests to take the place largely of human acceptance tests. There's no role for human regression testing at the kind of speed and efficiency and quality that we're talking about. Human beings are too slow, too low quality, not repeatable enough. So we're going to automate all of that stuff. Acceptance tests are tests from the perspective of an external user of the system, testing in lifelike scenarios, evaluating the system in lifelike scenarios in a production-like test environment. So we're going to deploy the software that we built into an acceptance test environment, run a bunch of high-level scenario-based tests against those. This is BDD, if you're familiar with it, acceptance test-driven development, specification by example, those sorts of ideas. If we are going to do any manual testing, it's going to be exploratory and just kind of, is the system nice to use? Does it paint pictures in my head that allow me to explore? And then we're going to add anything else, any other kinds of tests that constitute releasability, security testing, performance testing, resilience testing, data migration testing, any of those things that we care about on the journey before we're ready to release. The idea of a deployment pipeline, which is what I'm describing here, is to go from commit to releasable outcome. And that's what we're trying to achieve. And this is what we're trying to achieve in ideally under an hour, multiple times per day. Think for a moment what that would take for you to be able to achieve that. It's a big ask. Once we've got to that point, then we can happily deploy that thing into production. One more thing to say before I move on to the next section is people often confuse continuous deployment with continuous delivery. Continuous delivery is working in a way so that your software is always in a releasable state. The decision to release is a business decision and varies by business. For some businesses, it makes good sense to push things directly into production, which is continuous deployment. For others, it would be irresponsible. Continuous deployment is if all the automation says it's good, it just pushes the change into production with no human interaction. Volvo Trucks is one of the organizations that uses continuous delivery in a fairly sophisticated manner. There are 80 million lines of code in a modern Volvo truck. By adopting continuous delivery, they went from it taking 6 months to get a single line change into a truck on a test track to it now taking 20 minutes to achieve the same trip. And if I was a Swedish lorry driver driving down an icy road late one night in the middle of a thunderstorm, I don't think I'd want a software update at that point. And so continuous deployment would be irresponsible. But continuous delivery is still a valuable way of working because, you know, it's a business decision when you choose to release the change into production. Releasing more frequently gives you more opportunities, but it's a business decision. Around about this time in my conversations, I sometimes start to see some pushbacks. And the first one is, okay, that sounds wonderful. And I'm sure it's great for small, simple projects, but it can't possibly scale. My answer to that's the Google build process. They have literally millions, actually they're into the billions of lines of code now. They run hundreds of millions of test cases every day. There's more than 20 commits a minute that are evaluated, and all of their stuff is in a single repository. So if your problem is bigger than that, I'd be interested to talk to you because it'd be an interesting case study. But otherwise, this process will probably scale. The next one is, this is too risky. You're talking about releasing all the time. It's a recipe for disaster. My example for this is the Amazon build process. Has anybody used Amazon in the last couple of weeks? Which version did you use? That's a stupid question because even Amazon probably couldn't answer it. They are deploying, on average, a change every 11.6 seconds. On average, that change goes to more than 10,000 hosts. And they've been doing this for a while now. Since they've been doing this, they saw a 90% reduction in outages triggered by deployment as a result of moving more quickly. This is a risk reduction approach, not a risk increasing approach. The next pushback I get is sometimes this may be, okay, all right, fair enough. It works for simple websites like Amazon and Google, but my software is really hard. And my example for this, I chose this example. This is a bit of a dated example, to be honest, but the nice thing about this example is there's some data behind it, which I can show you. This is captured in a very good book, which I recommend that you have a look at. This is the HP LaserJet firmware team experience. Some years ago, they were in a terrible place. They had a backlog, a 5-year backlog of requirements, and 5% of their global software development effort went into engineering effort, went into creating new features, which they call innovation. 25% went into porting code, 5 times as much effort into porting code between branches as to building new stuff. They decided that what they were doing was just wrong and started to re-engineer their approach. They kind of came up with an independent path invention of continuous delivery. This was kind of in parallel with Jez and I writing our book. The bottom line is that they ended up with 8 times as much effort going into the creation of new software. That had a radical impact on the bottom line, the effectiveness of their software development. Programs under development were increased while the development costs went down. The cost per program was down by 70%. We are often talking, when we talk about the impact that continuous delivery has on organizations, orders of magnitude changes. We're not talking about a 5 or 10% increment here or there. I want to tell one more. I kind of assumed, talking to a bunch of people that are, probably there is a bunch of people that are London-based and finance centre-based. I thought it was worth just pulling out something that was here. One of the other pushbacks that I often get is, okay, I work in a regulated industry, this can't work. I spent most of my career working in regulated industries. And so my example for the regulated industry is my example. This is the LMAX process. This is where we built our financial exchange. So a little bit of characterizing this. We kept all of our entire enterprise system in a single monolithic repository. It wasn't a microservices system in terms of the way that we addressed the storage and deployment of the system. The system processed tens of billions of pounds in assets every day, and 1.3 times the daily volume of Twitter every day. We had continuous build and test on commit for any change to the entire enterprise system. Compliance and regulation were treated as sources of requirements. Any successful release candidate is automatically compliant and has a machine-generated audit trail to assert that this was the case. I want to contrast this. After I left LMAX, I went and worked for a trading company. And if you work in the finance industry, you've probably heard of Knight Capital and the Knight Capital disaster. The trading company I worked for ended up merging with Knight Capital, so it became part of my job to help Knight Capital and the organisation I worked for improve their software development practices. So I have a little bit of inside knowledge about what happened here. Knight Capital had one of those really, really terrible days. They were working in the trading industry, and one day they had an individual whose job it was to release some change into production. And this person had got to release the change to 8 different servers, and their process for releasing change was wholly manual. What that means, inevitably, in those circumstances, is that each of those 8 different servers was slightly subtly different from all of the rest. On this bad day, one of them was wrong in a fairly catastrophic way. There was a piece of software that was lying around dormant on this software that hadn't been run for several years. As part of the change that was being deployed to these 8 servers, there was one change that repurposed a bit in a message. In low latency trading, every bit counts, and so you don't add more bytes to add a new part to a message. If you can avoid it, if you can reuse it, you'll just repurpose it. So they're repurposing this bit. You should be feeling nervous by now. This bit accidentally switched on this dormant piece of software. This piece of software went crazy and started trading at completely the wrong prices in the New York Stock Exchange. By the end of the trade, so they turned it off after about 45 minutes of this code going wrong, by which time they'd mistraded $2.5 billion in assets. At the end of the trading day, they were able to manually unwind $2 billion worth of the missed trades. They were left with a bill for I've slightly understated it here, it was $450 million. So Knight Capital went bankrupt in 45 minutes because of a software mistake. I want to just characterize this and just kind of paint the picture of regulation. There are 3 levels of regulation that I would like you to keep in mind as I walk through this statement here, which comes from the Securities and Exchange Commission filing into Knight Capital. The first is the LMAX version, the automated continuous delivery approach. The second is the clearly inadequate approach that Knight Capital applied to making this change. And the third is the assumption of what good is in the Securities and Exchange Commission filing. So, reading the text on the screen. During the deployment of the new code, one of Knight's technicians did not copy the new code to one of the 8 SMARS computer servers. In the LMAX case, all deployment was wholly automated. We didn't touch production. The automation scripts, the deployment scripts touch production. So if it deployed it to one server, it deployed it to all 8 for sure. So the servers would have been controlled, version controlled. If there was a difference, which is hard to imagine how that would have occurred, it would have been overwritten when we re-released. If there was a difference that caused a problem, we would have had evidence of that difference because we had an audit trail that described all of that stuff. Going on from the text, Knight did not have a second technician review this deployment. All software development and all deployment and all releases were done in pairs at LMAX. When we deployed into production, we had a regulatory requirement that we needed a sign-off and approval by somebody representing development, somebody representing testing, and somebody representing operations. So we built that into our deployment pipeline. It wasn't possible for me to decide alone to release into production. We had to have 3 other people sign into the deployment pipeline and authorize the release of the change. It goes on in the text. No one at Knight realized that the PowerPeg code had not been removed from the 8th server. Again, in the LMAX case, if it was removed from one server, it would have been removed from all of them. Nor that the new RLP code, which the bit switched up, was flipping the switch, had been added. Knight had no written procedures for such a review. Well, written procedures are kind of quaint, but that doesn't say that the mistake couldn't happen. You could write the procedure and not follow it. You could write the procedure, you could falsify the procedure and write it afterwards. How much stronger is an automated audit trail of every interaction with the production system and all of the software that was designed, that was changed to go into that release? How much stronger is an automated audit trail of all of that stuff? If we start taking compliance seriously, then automation is the way to go. I've written some articles on the ideas of continuous compliance. I think that it's almost impossible to imagine being genuinely compliant, regulatory compliant, in the absence of continuous delivery. So not only can you do work in regulated environments with continuous delivery, it's the only way to really achieve compliance, in my view. The impact of this is dramatic. As I said, we're not talking about tiny changes. There's peer-reviewed approach to analysing software projects that says things like organisations that practice the kind of disciplines that I'm talking about spend 44% more of their time on useful, productive code. And this one that's left on the screen. Organisations that practice this kind of discipline have 50% higher market cap growth over a 3-year period than organisations that don't. So who practices continuous delivery? What sorts of organisations? The sorts of places that you'd think about: Google and Amazon, those sorts of places, Facebook, all of those sorts of things. But Capital One Bank, NASA, the Curiosity rover was using some of the ideas of continuous delivery. LMAX Exchange, where I work, the Department of Defense are using continuous delivery to deploy, the US Department of Defense are using continuous delivery to deploy changes to fighter jets. Volvo Trucks, Barclays Bank, ING, Siemens Healthineers. I worked with Siemens Healthineers on machines that kill people if they go wrong. In a heavily regulated segment of the healthcare industry, and we were using continuous delivery from them. ING Bank, SAP. These are names that may surprise you. Continuous delivery is broadly practiced, and it is increasingly at the heart of organisations that we think of as doing a good job in software development. That's my presentation. I've overrun by about 3 or 4 minutes. I'm sorry about that, but thank you for listening. And now I think it's time for the fishbowl and the Q&A. Thank you very much indeed for your time.
That's brilliant. Thank you very much, Dave. That was awesome. And you didn't overrun. You're bang on time, because I finished introducing you at 6:05. So perfect. Thank you. So what we're going to do now is we're going to run a fishbowl. I've asked everybody in the audience to take a look at the questions in the Q&A and vote up the ones that you would most like us to discuss. Steve is going to bring in the people that will kick off the panel. Our panelists. Alan, hi, I can see you joining. That's great. We've got Lindsay, fantastic. I think Ali will be joining us as well in a minute. We're getting a few people saying they have to drop off, but thanks so much for joining us. Thanks, Kevin. Thanks, Stephen. Thanks, Jess. So I'll just quickly go through the approach, like the rules, if you like, for the fishbowl. So as with all fishbowls, we'll do one person talking at a time. If you are not talking, make sure you are on mute. So this is best for an approach for doing it online. If you want to signal that you'd like to talk, so normally in the physical world, we'll pass around like a rugby ball, like a conch. But if you want to signal that you'd like to talk next, then just unmute if you're on the panel. And if you want to join the panel, so anyone from the audience is welcome to join. If you want to join the panel, then use the Zoom raise hand feature, and Steve will bring you in, and then he'll remove another of the panelists. I think normally it'll be the person that hasn't spoken for the longest. If you're a panelist and you really want to be removed, then just put a note in chat and Steve will pick that up. So audience, as I say, if you want any questions to be considered, we've got quite a lot already. Actually, the Q&A box, there's 12 there, which is excellent. But add them to the Q&A box. We're only going to run it for 30 minutes, so it's unlikely we're going to get through all those questions. And But what we'll do is we'll pick them up in priority order. So the ones that got the highest votes, we'll pick that up first, and we're going to finish the fishbowl at 7:30, because I know everybody is spending a lot of time on screens at the minute. So we'll make it short and sweet. So with that said, I'm going to scroll to the top, and we've got a clear winner for the first question to talk about, which is from Ollie Newsham. Thank you, Ollie. And how do you convince managers that loading the queue, and this is from earlier on in the talk, is a bad idea? So we're going to answer that live. Over to the panel.
Can I go? Good. So it's always difficult. So as technical people, the kinds of arguments that tend to land with us are probably more technical and more evidence-based. It's not necessarily what's going to convince people. The way to change people's minds are not necessarily rational thoughts, as we can see with the state of politics in the world at the moment. It's more about, you know, emotional ideas and those sorts of things. So you've got to do a bit of marketing. You've got to kind of bridge the divide between the technical and the business. You've got to put yourself in their shoes and think about what do they care about. And it's also what we care about, so it's not a big deal. So, you know, we want the organizations that we work in to be successful. We want to be able to produce software quickly and efficiently so that we can learn more quickly and make better software, and if we're a commercial organization, make more money as a result. These are good arguments that are going to land with people. The real question is, how's that been working for people? If people are doing feature, how's that been working out? Are they getting what they want? And usually they haven't. It's an incredibly difficult argument to make. I'm not trying to belittle it, but you've got to start getting to the rationality. There's another part to this. You've got to have those conversations. You've got to start putting the evidence. So one of the things that you can do is go out and buy Nicole Fosgren's Accelerate book and give it to your manager or whoever it is that's doing the features. That's going to make a really good, compelling argument for some of this stuff. But the other part of this is that we, as technologists, we also need to take on responsibility for our own selves. Very often, developers will say to me things like, "My manager won't let me run tests because you know, I've got to do all the features." And when I go and talk to the managers, they say, "No, we don't. We want people to write quality software. We're not ruling out writing these tests. And anyway, it's not their job to decide what's professional in software development. That's our job, and we must take responsibility for it. So if you were to employ me to write software for you, I'm going to do test-driven development. I'm going to write tests. I'm going to spend probably at least as much time writing tests as I am writing production code. But I think I'm going to be more. I'm going to do that because I think I'm going to be more productive for you if you employ me. And it's my professional duty of care to do high quality work. And so I'm going to make the decisions over what constitutes high quality work. I'm not going to rush stuff out that I know to be lower quality, because I know that's going to come back and bite me and make me slower overall. Remember, 44% more efficient. That's nearly twice as effective, as efficient, twice as fast in terms of the capability of deployment. So I'm going to, if I'm doing a quality job, doing all this testing, all of this thoroughness, I'm going to be producing higher quality software twice as fast, nearly. That's a huge win for any organization. So you start giving these numbers to people and they say, yeah, that's what we want. One of the advantages of continuous delivery, I think, is because the story, the stories that we can tell, the ideas align completely with organizations. Everybody wants to have an idea and get it out to the hands of users quickly and efficiently. Sorry, waffling.
Right.
Can I add to that? I think being able to see the queue and be able to talk to your manager about what the queue's current state is and help them understand the consequences of loading it, and give them some options as to if they're going to add kind of X more items to the queue, when are those items going to be picked up, and what other items it's going to impact can be helpful. If you're in a situation where you're constantly having to work with a highly loaded queue, then I think discussing with your manager about running an experiment where you try out having a less loaded queue to start off with for a period of time, and whilst you're running that experiment, gather some data in terms of does it increase the throughput or does it slow things down. That can be useful feedback for both you and the manager as well.
All right, we'll give it another the regulatory 30-second awkward pause for online for anybody else to jump in before I move on to the next question.
I'll make one addition. Lindsay's was a really good point in that you know that you're winning with this stuff when your product owner or your manager or whoever else comes up and they reorganize your board for you without having to talk to you. It's a really good sign when they understand the trade-offs when they're moving things down.
Okay, great. So we've finished with that question. So the next one that we've got here is from G. Stober. Apologies if I'm pronouncing it wrong. And what business practices, processes must change to achieve continuous delivery?
Ownership. Sorry, Dave, do you want to go? I was going to start with ownership. My experience is giving the more ownership you can give a delivery team of as much of the end-to-end software process as possible is the biggest enabler. So if you have current business practices or processes where people outside of the team are setting priorities or deciding when something can be released or whether it's appropriate to be released, those things are inhibitors to continuous delivery. That's where I would start.
I think I'd go a little further. In some organizations, I see ownership for outcomes of the work is often, the work that's done might be defined by a product arm of the organization, but the ownership for the outcomes is IT's responsibility. And as soon as that ownership becomes shared or becomes the responsibility of the product organization, then they're much more interested in getting that return on investment sooner and in a more iterative manner, which CD facilitates.
I think it's seriously radical. I think it touches on nearly every aspect of the way that teams work, the way that that they're directed, the way that they're incentivized. All sorts of things can have an impact that adversely or adversely impact on the ability to deliver, to continuous deliver or promote it. So there's a vast amount of change. But I think one of the nicest catches of a really important set of ideas that I saw was from an ex-colleague of mine and friend, Gregor Hope, who used to work at ThoughtWorks. We used to work at ThoughtWorks together. And he did a great talk in Singapore a couple of years ago when he was talking about the role of kind of senior architecture, senior technologists in an organization. And he came up with this slide in terms of what you optimize for, and he broke the slide. There's a bunch of stuff. There's a bunch of learnings on the slide. It was a really good slide. But one of the things that he came up with, he said, one of the things that you can tell about an organization is where do the senior technologists report? Who does your CTO report to? In most traditional organizations, they report to the finance director. And in which case, the tools that they use to optimize are to cut costs. They see IT solely as a cost center, and all they're doing is work to cut costs. The next step up from that is that they report to the COO, which is a bit better. But what they're then looking to do, the way that you optimize for that is kind of standardization. So you know, in the first case, they'll probably be outsourcing to cut costs. In the second case, they're going to try to make sure everybody's got consistent tooling or processes or something like that. Then you start getting further up, and when you get into the organizations that are really, you could generally start to think of as digitally disruptive, It stops, IT is no longer a subservient function. It's not a cost center or an operations function. It is the business. It's the driver. It's the difference between digitally disruptive businesses and more traditional businesses is information technology. And then what you optimize for is speed. So continuous delivery is about optimizing for speed. It's the tool of digital disruption. It's not an accident that some of the most disruptive organizations, Netflix, Amazon, Google, those sorts of places take continuous delivery and its approach really, really, really seriously, invest in it massively. It's because it enables the business to go. So they don't look like conventional businesses, so it touches on almost everything.
Okay, great. And I suppose it also depends where you're starting off from as well as to what might need to change to enable continuous delivery. Ali has had to drop off. If anybody in the audience, I don't think anyone's put their hand up yet to join the panel. If you do want to raise your hand, then Steve will bring you in. But in the meantime, I will mark that one as done. And the next question with the next most votes. Interestingly, a pattern here is the shorter the question, the more votes you seem to get. So for future expert talks, bear that in mind if you want your topic to be discussed. Omkar, which is actually a great thing for me because there's less to read out. So Omkar Karmarkar, yes, sorry, apologies for the pronouncement. Do QA responsibilities change in continuous delivered projects? So do QA responsibilities change in CD?
John?
Yes, it is. It's 18 votes.
Okay.
You got a different view to me.
I do.
I'm happy to go if nobody else is.
I think my experience is that QA responsibilities become shared, so everyone in the team becomes responsible for quality. And then secondly, quality is thought about much earlier in the cycle. And so it's, instead of the kind of engineering a feature to be like a mini waterfall where there is a distinct test phase, people are thinking about testing and quality when they're describing the feature and when they're doing the business analyst, they're thinking about how are they going to kind of validate and measure its impact on both the kind of running production system and the business as a whole. And then that thinking about quality kind of goes throughout the team. So in a team that's practicing continuous delivery, I think you should see much more blending of the roles and responsibilities. What do others think?
I think something that Dave talked about as well. I see the QAs taking more of responsibility for shaping what the pipeline looks like, because I can't remember the exact wording, but one of the things you said, Dave, is everyone's continuous delivery pipeline looks different depending on what the constraints, what you're optimizing for your organization, and that's going to change over time. And the QAs have an active role in defining and optimizing that pipeline to match the requirements, the constraints of the organization. Much more so than a more traditional role, which is, oh, the software's done, now it's time to take a look at it.
Yeah, I agree completely with what Alan and Lindsay said. I think it does change the QA role. I think it changes. It changes it. There's kind of I'm starting to believe that there's kind of a pattern in the way that specialist roles work in general. The sorts of teams that really fly at this kind of stuff, the responsibilities tend to become team responsibilities rather than responsibilities of any given individual or role. And so the team takes on the responsibility for the quality of the software. And then the roles of expert practitioners in almost anything, security expert or a QA expert or whoever, is to help the team get better at that responsibility. So the QA is not the responsibility, quality is not the responsibility of QA people, it's the responsibility of the team, but a QA expert can help enhance the quality, the understanding and the applicability of the team. I've been doing some stuff about DevSecOps recently, and the same thing is true. You know, a security expert can enhance the thinking on the team of security understanding, but you don't want them to be a gatekeeper.
Yeah, that was basically why I put my hand up, is that my experience has been, and apologies, I was also kicked out at the moment. I was joining the panel, so I may have missed some of the conversation, but it was basically the idea that some of the real strength I've seen with QAs in that distributed quality environment where everybody is focusing on quality is that mentoring aspect. So working with the BAs to make sure that the definition of what we should be trying to achieve is measurable and is testable. All the way through to, as Dave was describing there, the other aspects of quality, be that performance or monitorability and all these things. They're all transformed quite dramatically, actually, to be advisors and supporters of everybody else who was now involved and responsible for quality.
Almost to the extent that, taking it to the extreme, if a QA is doing an awesome job, they almost don't need to exist anymore. You know, if the QA is not there anymore, but they've trained the team, or they've coached the team in how they can do everything they need themselves, then that's a great result.
And also the other thing I've experienced is when you get to that place where the team are just automatically generating quality products, the QA then goes to the next level higher, which is similar to what the BAs tend to do, is go, well, what more can I understand about the system and the impact? So their level goes beyond. Again, the developer might be focused on a specific thing here and now, and the QA is actually recognizing things that they can't possibly think of. And again, it really creates a continuous kind of cycle of improvement of the way the team works.
All right, excellent. So there we go. Thank you. So I'll zoom on to the next one. We might get one, maybe two more in. Another one from Omkar. How do you deliver big features? This is a very practical one. How do you deliver big features which can't be broken into small pieces? Do techniques like feature toggles always work? Are there any other techniques?
There's a family of techniques to do with this, and these are kind of almost forced on you when you start really taking continuous integration seriously. You start doing trunk-based development and working on a single branch to production. It kind of forces you to think about how you can decompose features. So the first thing to do is to try and figure out, is there a way in which I can kind of divide the requirements up into small enough pieces that I can, do these things very simply. There's a great book from a friend of mine, Gojko Adzik, called 50 Quick Ideas to Improve Your User Stories. And I keep a version of that book on my iPad so that when I get stuck, I can refer to it, because it's got a section that tells you a whole bunch of suggestions about tricks to decompose user stories into smaller stories. And it's just brilliant for that. So that's trick one. And then you get to the technical things. So, one of the techniques that we talk about in continuous delivery is separating deployment from release. So I can comfortably deploy stuff into production that is not yet released. And there are three techniques that really support that. One is called dark launching, meaning that basically I put stuff into the production, but it's not wired up so anybody can use it yet. And the next one is branch by abstraction, where we're going to put seams in our code where we can kind of plug in different behaviors. You may imagine being able to run two different versions of the software in parallel with one another and kind of see, measuring them while in production alongside each other and all that kind of stuff. And the last one, which everybody's heard of, is kind of feature toggles. And I generally advise people to do them in that order. So first do dark launching, then do branch by abstraction, then do feature toggles. Feature toggles are good, but they make me nervous if you have too many of them. So if you've got one feature toggle, what do you test before you release? Do you test it with the feature toggle turned on or off? Then you might say, I'll test it with both to be safe. And then what happens if you've got 500 feature toggles? The explosion of complexity as the number of feature toggles goes up, the paths through your code base means that you quickly get to an untestable surface area. And so now you're releasing stuff into production that you don't know whether it works together or not. So I would think it's, as a guiding principle, it's a good idea to limit the number of feature toggles that are in use in production at any given time. But feature toggles are a perfectly fine approach to being able to drip changes into production before you've actually assembled a whole big thing.
That's great, thanks. I was just, Alan beat me to it. So Luis Suarez just asked, what's the name of the book that you mentioned? Alan has put it into the chat. Thanks, Alan. You beat me to that. Excellent. So I think let's just see if we can get one more sneaky one in. Yeah, because it applies to the Q quality assurance, which was Ollie Newsham is asking, how did you manage the manual testing element in the 57-minute cycle diagram that you showed?
I kind of cheated. It wasn't in the 57-minute cycle. The way that we worked was that the 57-minute cycle was the automated evaluation. Manual testing was our manual testing was largely carried out by QA people, the exploratory testing, and they were sat next to the development teams. They were part of the same teams, working extremely closely, and so we were doing the kind of, you know, drip changes. So we were separating deployment from release. So our software was always releasable, but a feature might not be finished yet. But testing also worked on the same basis. So when you get to a certain point, oh, you could now go and test this bit, and so they could go and test a piece. So they were still testing ideas very often before they were actually released, but there wasn't a gating process in the deployment pipeline. That was acceptable because if you think about it, if we are running tens or hundreds of thousands of automated tests that evaluate our software in our deployment pipeline in all the ways that I described, then the kinds of bugs that a human being is going to find are going to be, you know, the color's wrong, or, you know, I've got green text on a green button, or that controls off the screen a bit. It's that kind of stuff. It's not going to be functionally broken because the testing covers that. And so you can probably survive accidentally releasing one of those changes into production. The software's still going to work. It's still going to be safe. It's still not going to kill anybody or lose anybody money. It just might not be as pretty as you want. And so I'm undervaluing the cost of the exploratory testing. But you can see it's a different class of bug that human beings find versus the automation when you've got the kind of automation that I'm talking about.
All right, excellent. So we are at the half past, and think we will close it there. There's still another 10 questions, loads of questions coming in, so lots of really engaged people. That's brilliant. So I'd just like to say thank you, Dave, for joining us this evening, and remind everyone, go and have a look on YouTube, search for Continuous Delivery on YouTube, and Dave's channel is the first thing that comes up. So have a look and see all the great content that Dave's publishing there. We're going to be running, the rest of June, we're running a whole series of talks about continuous delivery. Next up, actually, we had a little switcheroo. Lindsay, I think you're up next week, is that right? Excellent, with a tale of smoothing the path to continuous delivery with 2 different architectural approaches. And we will be sending out the recording, we'll be uploading the recording list onto YouTube and sending that out to everybody that joined this evening. So thank you very much for joining us. I hope you can come along next week. I will see you later. Thank you very much. Thanks, Andy, and thanks, Alan, for taking part in the panel as well.
Thank you, everybody. Thank you.
Thanks, Dave.
Bye.
Cheers. Thank you.